Shit, ich habe vergessen die. Könntest du nochmal die Evaluierungsbögen rüberdrehen? Ja. Danke. So, welcome to today's lecture. We have last time dealt with, after branch and bound, we had looked at special cuts, the Gomori cuts, to check linear equation and inequation systems over integers. And we have the Gomori cuts we have seen last time, we discussed with an example in the exercise. So we do not continue with that now, but we continue with another method, the omega test. So we have already seen two versions of using simplex for integer valued constraint systems. And the reason why we look at still another procedure is because those methods are not complete. Though the theory is decidable, so there exists an algorithm that gives for each problem an answer to the satisfiability question. But those methods which we have seen by simplex are not complete, so we will look today at another one. It is called omega test, and this is complete. So our goal is, as before, we have a system of inequations and equations where the variables range over the integers, and we allow only addition. That means these are linear constraints. Multiplication with constants is, of course, allowed. This can be led back to addition. The original application of this method was to optimize programs. So they optimize the compiler, which generates machine code such that the executables which are generated are efficient. They use it in a general framework, and basically this is similar to the Fourier-Motzkin variable elimination, which we have already seen, but it is an extension. So we will still use variable elimination, similarly to projection, so projecting out dimensions. And the main advantage of this method is that it is incremental. As you will see, it consists of 4 stages. There's a pre-processing stage, then 2 stages which are efficient but not complete, and last stage which is not so efficient, so it needs more computation, but then at that stage the algorithm becomes complete. So you see we have here inequations and equations, and the basic method can only handle inequations. So in the first step, we will use a pre-processing stage where we first simplify the problem, and second, we eliminate equations. So let us look at this first stage. We will see later that the efficiency of the method depends on the coefficients. So if we have large coefficients, then especially the last stage will be very expensive. That's why we are interested in making the coefficients as small as possible. So in a pre-processing stage, for example, from this inequation, we can conclude that if we divide by 2, then another constraint with smaller coefficients can be generated. This is done for all constraints in the system. Another point is if you have 4y is larger or equal 1, we have an idea how we could make a more restrictive constraint from this. So now in the first example, we could divide by 3.
Y is an integer, then y is also larger or equal to 1.
Exactly. So if we have constraints where we divide by a common divisor of the coefficients, And on the right-hand side, we have a constant. If we divide this constant and this is not an integer, then we can use, according to the comparison sign, either the next largest to the next smaller integer. So from y larger or equal 1 fourth, by dividing by 4, we can imply that y is larger or equal 1. Yeah. Let us continue. Yeah. So there are only 2 people working who came a bit later. You have here an envelope afterwards. At the end of the lecture, you can just put it in.
Yeah.
Danke. So we were, by the omega test, eliminating, simplifying first constraints. So this is called titling. And if I have such an equation, 3x plus 3y equals 2, what can I do then? So we work on integers. How can I reduce this equation if I know that there are integers? I tried by dividing by common divisors of the coefficients. So in the first case, I could divide by 3. In the second, by 4. And here I can divide by? Exactly. So I can divide by 3, and I get that x plus y equals 2/3. And this is, of course, unsatisfiable. If x and y are both integers, then the sum can never be a non-integer value. So by reducing the constraints, I can already get some answers to the satisfiability question. Of course, in general, it will not be the case. And there will also be some equations where I cannot reduce such equations because there are weighted sums. Like, so in this case, I can get answered. But in general, I can have such sums of equations. And my problem is that if I have, let's say, no common divisor, only the 1. Let's say if I have 2x plus 3y equals, let's say, 1. 1 is not so good. No, yeah, it is also satisfiable. Or another example is, which we will take later, is 4x plus 3y equals 7. What is the problem in this case? Why we cannot apply the previous simplification method? Now, the largest common divisor of my coefficients is 1. So I could divide by 1, but it doesn't help. If I could divide by a by a value which is not a common divisor of the coefficients, then the problem is that I get non-integer coefficients. And this is not good because then I cannot apply the method later. So what I would like to have, my problem is that I have equations and inequations with integer coefficients. So in this case, there are, of course, special cases where I can reduce. If I have, for example, the equation x plus 3y equals 7, then I can use this too. Then I can use this equation. How would you do reduction with this last equation, x plus 3y equals 7? You can just eliminate this equation by if you have equation systems, normal equation systems, then how do you solve it? The most natural way to solve equation systems, let's say over the reals.
Take x equals 7 minus 3y and apply it to other equations.
So you can reformulate such that one variable is separated on the left-hand side and the other terms on the right-hand side. And then in each other constraint, equation or inequation, you can just substitute 7 minus 3y instead of x. It does not change anything since we have an equation. So the values are equal. And then you have a new system where x does not appear anymore. So you reduce the dimension and eliminated the equation. But if we have such an equation where you do not have coefficient 1 for any variables, then it is not trivial hard to do this. And for that there is a trick. We pick one variable and make its coefficient positive. So for example, if I have this example 4x plus 3y equals 7, I can pick any of the variables x or y, and its coefficient is already positive. And now we need something which is in the first moment not so intuitive, but you will see later that it is very efficient. We define a modulo operator. And this modulo operator is not quite the modulo operator you know, but it may push the results with the value b to one of the directions. To understand it, let us look at an example with modulo 4. So the modulo is a minus b times a divided by b plus 1/2. And this plus 1/2 is what is special. So if I have here the let's say, to have a concrete example, it is easier to understand, we take modulo 4. So this is 4. For these values, let us compute the modulo 4. We start with minus 4. Minus 4 modulo 4 would be, I just write it down as in the equation defined, minus 4 minus 4 times minus 4 divided by 4 plus 1/2. So this will be here 1. And that's why minus 4 modulo 4 is 0. So I just, sorry, minus 4 minus, yeah. Sorry. So it is 0. That means normal modulo would have been 0 because the rest is 0, but it is pushed. In this case, the two operators modulo and het modulo are the same. It is the rest. But by minus 3, we will see the definition is just minus 3 minus 4 times minus 3 divided by 4 plus 1/2. And this is now minus 1 still. So we have in this case plus 1. This would be a kind of mirrored modulo. By minus 2, you can guess that this will be, oops, sorry. By minus 2, we have minus 2 minus 4 times minus 2 divided by 4 plus 1/2. So this is 0. That's why it is minus 2. By minus 1, it is again 0, so it's minus 1. And if you continue, then you see it is just 0, 1, and then by minus 1, minus 2 again. These are the het modulo 4. So what we have is that it is a kind of modulo, but the rest is shifted. Normal by modulo 4 you have rest 0 to 4, but here you have rest minus 2 to 1. And the reason why we do this is to get smaller coefficients as if we would take the normal modulo operator. First, we look at the rule, how we use this modulo operator to eliminate the equations, and then we will look at an example that you see how the coefficients are indeed reduced. So what we do with this modulo operator, first recognize that if I have a coefficient ak and I define m as ak plus 1, then ak modulo m is always minus 1. So if I have an inequation and apply this modulo operator to all coefficients of variables, then at least one variable will have the coefficient minus 1. That means, since it is an equation, I can use this equation to eliminate this variable. So if I have an equation, Ixi equals b, then I just make modulo to a coefficient on the left-hand side for each equation. And I do not know how the sum is modified, because you see that the modulo shifts the result by, if I have modulo m, the result can be shifted by m. But I know that the actual modulo parts are in this expression, so to the normal modulo it is just shifted by a multiple of my modulo operator m. So that's why this equation holds. It does not have to do for the first anything with the original equation, but I know that there exists a sigma such that if I take the coefficients modulo m, then I change the sum just by a multiple of m. So I do not know how many times, that's why I introduce a new variable sigma. But the old sum, where the coefficients are this het modulo m, equals b het modulo m plus a shift of a multiple of m. And since I do not know this multiple, I just introduce a new variable sigma. So I just introduce the new equation. And we said in the previous slide that if I take m to be one of the coefficients ai plus 1, then one of the coefficients, one of these modulos will be minus 1. So I can use this equation to eliminate one of the variables. In this example, this was xk. So what we do now is we introduce a new equation. If I had n equations, I still have n equation, but I have a new one. And I can use this new one to eliminate one of the variables. But I also introduce the new one, sigma. So what is the aim of eliminating one variable and adding a new one? The aim is that we reduce the coefficients. So this modulo, as I said, is shifted. That's why the coefficients, by applying it, will become smaller. Okay, let us do an example. We have this equation, 4x plus 3y equals 7. Now I can take basically any coefficients. I just take the 3 of the y, because as we will see, this is optimal. But I could take also the 4 of the x. So I take, if I take the smallest coefficient, then it is usually the most efficient. So what happens? Now we said I will compute this coefficient plus 1, this modulo. So what I have is this het modulo 3 plus 1, which I compute. Okay, compute it first for this sum, and this will be 4 het modulo 4x plus 3 hat modulo 4y equals, and now I introduce this sigma, 4 times sigma, plus the 7 modulo 4. Okay, let us compute it. 4 modulo 4, we can just check, we computed it already here. 4 modulo 4 was 0. So this is 0 times x plus 3 modulo hat 4 is minus 1. And it equals 4 sigma plus 7 modulo hat 4 is also minus 1. So what I get is y equals minus 4 sigma plus 1. I can use now this equation to eliminate y in the previous equation. So from 4x plus 3y, I get 4x plus 3 times now this term equals 7. Equals 7, yeah. So 4x plus minus 12 sigma plus 3 equals 7. So 4x minus 12 sigma equals 4. I can divide by 4. This is always the case at the end. So I have x minus sigma equals 1. Or x equals sigma plus 1. And if you compare it now to the first equation, then you see that the coefficients are reduced. And we can also check that the set of satisfying solutions is the same. So let us look at what are the satisfying solutions of my original constraints. I have, for example, minus 8 and 13, or minus 5 and 9. So always the x must change by 3 and the y must change by 4. Then I always have that the sum does not change. Then the next is here minus 2, 1, 4, 7, and so on. And y is always 4 less. And so on. So these are the satisfying solutions. And now we can check that for each of them there is a sigma which fits. That means that the sigma replaces x, but it does not restrict its solution set, neither extending nor reducing the set. So if I have minus at 13, then I can just compute basically from here, sigma equals here minus 3. I can use here now just to compute the non-integer coefficients. Usually we do not do such transformations, just to show you that there are always values for sigma which satisfy and which are indeed integers. So by minus 5 we would have minus 2, minus 1, 0, 1, 2, and so on. Yeah, you see that exactly there it is the role of sigma. This is somehow encodes the amount of multiples of 4 which are the amount of values which are shifted from x to y in order to satisfy the equations. So if I have for example, minus 3, then you see x is 3 sigma plus 1, and a similar way I can compute here y is minus 4 sigma plus 1. So in the one equation I have 3 minus 4, and the equations should both hold. That's why by changing the value of sigma, I will always get a corresponding value for x and y. And now to show you how a bit more complex examples can be also handled. If I now extend this system, it fits well to the question, do we have integer or natural numbers solutions? I can now require that the solutions are natural numbers by additionally requiring, perhaps I take another color, that both x and y are non-negative. So I only would like to eliminate the equations. That means I will handle this the same way. I will get this constraint, and I can use it to eliminate x. And I use it, of course, also to eliminate x in the inequations. So from x larger or equal 0, with this equation, I can get that 3 sigma plus 1 is larger or equal 0. That means that 3 sigma is larger or equal minus 1. Then I'm done with the elimination of x, but now I can continue, and I can eliminate using this equation. I will apply again the reduction that we have seen at the beginning. So 3 sigma larger or equal minus 1, I can divide by 3, and I will get that sigma is larger or equal minus 1/3, but from that I get that it is larger or equal 0. And from here, y equals minus 4 sigma plus 1, and y is larger or equal 0. By eliminating y, I will get that minus 4 sigma plus 1 is larger or equal 0. So I will get that 4 sigma is less or equal 1. And similarly, I will get that sigma is less or equal 0. And using these two constraints, you see that the only solution is here. That means if I search for non-negative solutions, then the only solution which exists is 1, 1. And I will get it again already by eliminating the equation. Okay, so assume now that we have eliminated all equations and we have only inequations. That means I have, as before, inequations of the form, let's say, less or equal b. It doesn't matter because I can just change the sign. And now I would like to solve it. So we have 3 stages: the real shadow, the dark shadow, and the gray shadow, it is called. The real shadow is called real shadow because we just check for real solutions by releasing the integrality constraint. So what do we do here? We search for real solutions. For example, we could use simplex here. What we will do is using the variable elimination that we are used to in our, that we have got known to in previous lectures, but it doesn't matter which solution, which decision procedure we use here. We just check if there are real solutions, and of course if there are no real solutions, then we also do not have any integer solutions. Otherwise, if the real shadow finds a real solution, then we still do not know if there are integer solutions. And we will develop a condition which assures that there exists an integer solution. So if this condition holds, then we get an integer solution. So this way we can get some. But if this condition does not hold, then we do not know if there are still integer solutions or not. And this we will check in the gray shadow, which gives us a complete answer by either finding a solution which were not found in the previous stages, or it shows that the problem is unsatisfiable. So let us first look at the real shadow. This is, as we know from the previous lectures, if I have two inequations, so Z is now a variable, and B and C are integers, integer coefficients, and these are terms. Linear terms. This is our variable, and this is again an integer coefficient. Then we have seen that now I have a lower bound on Z and an upper bound on Z. So basically I can check if these bounds define an empty interval. If this is the case, then there are no solutions, and if the interval is non-empty, then there exists at least one real solution. So this was the elimination procedure what we used. However, what we did previously is that we divided by B in this equation. We divided by C in this equation such that we had set the variable on one hand side and the bound on the other hand side. We make a bit different now. Instead of dividing, we multiply, such that we have a term in the middle, which is common, having lower and upper bounds. Why we do this? Because with this way we can exclude, in some cases, intervals which do not contain any integers. Basically, the idea is similar, but this way we see a bit more. So for each inequation pair, making a bound on a variable, let's say Z, I can define a satisfying relation in the reals if the bounds define a non-empty interval that is satisfiable. If not, then it is unsatisfiable in the reals. So let us have a look at an example. We have three constraints defining this polytope as a solution space. And you see that actually there are no integer solutions inside. The reason is that the haze of this polytope here does not contain any integer solutions. So we apply now variable elimination, real variable elimination, in that first we eliminate x. This is just a choice. We define an order. We have two variables, x and y, and we can eliminate one of them first. Let's say we choose now x first, and these are the two constraints containing x, one defining a lower bound, one defining an upper bound by multiplying with -1. And instead of generating as before the constraints 2y less or equal x by dividing by 2, and here x less or equal 2y plus 3. I could do this now because the coefficients would not become non-integer, but instead we just multiply. Now in this case I do not need to multiply because the coefficient is the same. So I keep this one, and here I get 2x less or equal minus 4y plus 6. So you see, if I eliminate for 2x, then I get minus 4y is less or equal 6 minus 4y. So now I have two constraints. This is left, and this is the second one, which contain now only y. So I also eliminate y. And if I do this, then here I have a lower bound. And from here I have an upper bound. Namely 8y less or equal 6. So I will multiply this one by 2, and then I get the constraint sorry, I go back, the constraint that 1 is less or equal 6. So what I get from the real shadow is, sorry, I have to, so from that I'll say 2. Multiplying by 2, I get that 8y less or larger or equal 2. From here I get that 8y is less or equal 6. So I get and I do reduction. So by dividing by 2, I would get this, and dividing by 4 in the last dimension, I would get this. And you see that if I take, actually divide by 4. So I have get a lower and an upper bound, and the point is at the end, if I have only one variable left with lower and upper bounds, which are constants, then I can compute those bounds. And if I see in the last dimension that there are no integer values in it, then I see that there are no integer solutions. So if you look at the picture here, first we eliminated the x dimension. So what we get is a kind of projection here. That is, it is called the real shadow. So I get the complete real solution space. And if I see that in this interval, in the last one-dimensional case, that this interval does not contain any integer solutions, then I already can conclude that there are no integer solutions at all. However, I do not get always this result. If we now change the variable order and eliminate y first and then x, then I would first eliminate this dimension and I would get this solution space where I see that there are integers in it. So let us look at this case. If we eliminate y first instead of x, I have two constraints containing an upper bound, and I have one constraint containing a lower bound. So I will do both pairs. First I take this red one and the yellow one, and I see that 1 is less or equal to x is the result. And if I take the other pair, the lower bound with the second upper bound, then I get 1 is less or equal minus 2x plus 6. So far so good. Now I have two inequations containing one variable left, so now I check for the results. And here I get 1/2 less or equal x, and here I get x is less or equal 5/2. And this is exactly 2.5 and 1.5, so I get this bound. And there are integer solutions in it, so I do not know if the problem is solvable in the integers or not. I only know that it is solvable in the reals. So in this case, in the second case, I must continue. I know that there are real solutions, but I must still check if there are integer solutions. So this first check can give us only unsatisfiability answers.
So that could be good for all variables?
One after the other. So we eliminate each variable one after the other till you have only one variable in your system, and there you can check additionally to simplex or what you do in the real. You can check if the last interval there are integers in it. And if there are no integers in it, then you know it is satisfiable in the reals, but not in the integers. And if you get an empty interval, then you know that it is also not satisfied in the reals. Yeah, so if you have x1 to xn as variables, then you first eliminate x1, then you have only x2 to xn. Then you eliminate x2, and so on. And at the end, you have only one variable xn.
Yes, but when I find out that this has integer solution, do I then continue to eliminate until I have only xn minus 1 left and so on, or do I go to the next step?
you can only stop if either you see that there are no solutions at all, so you get an empty interval for a variable, or if you see that you get an interval with constant bounds and there are no integers in it, then you know there are no integer solutions at all. But if in all other cases you do not know if there are an integer or not, in this case, you see we projected first y and then x, and you get at the interval, at the end, you see here an interval for x which contains integers 1 and 2. But there are no integer solutions because in the earlier phase, by projecting out y, you projected out an interval which did not have integer solutions, but you do not see it there yet because these bounds are defined in terms of x. So these are sealed terms and not constants. What would be complete if, even that would not be complete. If you would take all possible variable orderings, then perhaps, I'm not sure, perhaps then you would get, if all intervals contain an integer, after all variable orderings, perhaps then, but I'm not sure, perhaps even then not. Okay, so from this phase, from the real shadow, I can only conclude that there are no solutions, but it is by no way, there is no way to assure that there exists an integer solution, even if there exists one in the last, after the last projection phase, in the for the one-dimensional problem. So if the real shadow tells us that there are real solutions, then we go to the dark shadow. And as I already mentioned, in the dark shadow we define a condition such that if this condition holds, then we know that there is an integer solution, and this gives us also an integer solution which we can compute. But if this condition does not hold, then we still do not know anything. And it is called dark shadow because I just will come back here. I would like to show you the picture of the example. Here. The dark shadow is basically, let's say, assume the projection of this solution to the x-axis is here. This is a projection, which is called shadow in this case. And if this haze has a kind of minimal haze, which assures you that there exists integer in all dimensions, then you can imagine that this shadow is darker. Yeah, the bigger the haze, the darker the shadow. And that's why the shadow here at the side is not so dark, it is called gray. And the shadow in the middle, where the haze is higher, assuring that there exists an integer in the other dimensions also.
I don't know what the word haze means.
The haze is at this point this, at this point this, at this point this. Yeah. Die Höhe.
Ah, hi. Okay.
Okay, so the higher the object, the solution space at a certain point is, you can imagine the darker the shadow. Yeah? So now I go back. That's why it is called dark shadow. And the dark shadow starts from the same setting as the real shadow, so we have lower and upper bounds on variables. But instead of now multiplying with b and c, we divide. And we allow these integer coefficients as bounds, where beta and gamma are terms. So these are just linear weighted sums of variables. And now we make an assumption. We would like to prove that there is an integer between this lower and upper bound. And to prove it, first we start from the other statement, namely assume that there is no integer between these two bounds. And if there is no integer between them, then we know that there exists an I, such that both values lie between I and I plus 1. And furthermore, we know that this difference here is at least 1 divided by b, because if it would be less, then it would reach I, and then I would be a solution. The same, with the same argument, this difference here is at least 1 divided by c, so the value of gamma must be at least 1, because if it would be smaller, then again I plus 1 would be in the interval and I would have an integer solution, which would contradict to my assumption that there is no value set between the lower and the upper bound. So both these values are strictly between I and I plus 1. Otherwise I would have an integer solution. So I just write it down. That means beta divided by b minus I, this is this distance, is larger or equal to 1 divided by b. And I plus 1 minus gamma divided by c, this distance is larger or equal to 1 divided by c. Now I have some reformulations. First I add up these two equations. Then I reformulate it by removing the fractionals, so multiply by c and b. It is just normal computation. Then I bring c times b to the other side, and I multiply by minus 1. Okay, I bring this to the next slide. This is the last one from the previous slide. And now I know that this holds if and only if not the negated relation holds. Now I know that I talk about integers, so this is larger than this. If this is larger or equal to this plus 1, all terms must be integers. And I finally can reformulate the right-hand side to a product. And now we are basically done. So again, what we did, we assumed there are no integer solutions, and we get a condition, then it is implied that this condition must hold. So I just write no integer solution implies that star does not hold. Yeah? Star is without the negation. So we know from the implication that means that if star holds, then there is an integer solution. And we are done. So we just check star, this inner inequation, if it holds or not. And if it holds, then we know that there is an integer solution. However, note that if it does not hold, then we do not know anything, because these formulations were not equivalent reformulations, but only implications. Here this slide is equivalence, but in the previous slide here, it was only an implication. Okay, example. I just removed this dark one. We have again an example with 3 inequations, and again we have to determine a variable order. We start with y. We have again lower and upper bounds, and on y we have 3, so 2 upper bounds and 1 lower bound. This is the lower bound, this is upper bound 1, upper bound 2. And I go back to the previous slide. Here we check this condition. Beta gamma minus c beta larger equals c minus 1 times b minus 1. So if you just believe me that if I apply it, then you get this inequation. So this is here beta this were our original formula. Beta is less or equal b times the variable, and c times the variable is less or equal gamma. So that's why here this is beta, b times, oh sorry, we have to reformulate. So I want to eliminate y, so I have y is less or equal, 2 times y is less or equal, yeah, this is beta, B y less C y less than or equal gamma. That's why. This is the upper bound, gamma. The coefficient is C, and y is my variable. And this is the lower value, so this is beta is less than or equal to B times my variable y. And if I substitute this B beta C gamma in my inequation, then I get this one. If I reformulate, then I get 8x plus 4 minus 6 is larger or equal 3. So from this I get 8x is larger or equal 5. Especially since we have only one variable left, I can check x is larger or equal 5/8. And if I apply my condition to the second pair of lower and upper bounds, then I get this inequation, and I can again compute minus 8x plus 20 minus 6 larger or equal 3. So minus 8x is larger or equal, what is this, 14? Is it minus 11? Yeah. Yeah. So x is less or equal 11/8. So this is the result, and we see that our condition holds. So these bounds can be kept, and we have an integer solution. And this allows us even to compute the integer solution, namely this is 1 lying between 5/8 and 11/8, so 8/8. But again, if we would change the variable order x and y, perhaps we would not find this solution. And in some cases there are integer solutions, but we do not find them because they do not lie in this dark shadow. So in this case, we will check the gray shadow, and the gray shadow is just the complete real solution space without the dark shadow. And as I said, this gray shadow is more computationally more complex because we will check each possible integer value in this gray shadow. So we have the real shadow, we take away the dark shadow, and we will check the real shadow without the dark shadow. Let us just look what it is. We know that it is in the real shadow. So again, if I have b times, so beta is less or equal b times my variable, and c times my variable is less or equal gamma, then I get this inequation by multiplying both sides with c, respectively b, and I have this inequation. This is the condition for having a solution in the real. And now we have the condition for having integer solution in the dark shadow. I just negate it, and I get, this is the first condition, I get the second condition. And I can reformulate it and use the combination of both to get this condition. So there exists an integer solution in the gray shadow outside the dark shadow if this condition holds. If there exists an integer value, c times b times an integer value between these bounds. And note that these bounds can be computed. So I can reformulate it how to compute, how to list all possible integer values in this interval. I just divide by c both sides. This is from the previous slide. And now I need all possible values set which lie between these two bounds. And how do I do this? First, I can try all. An optimization is that first I search for the largest coefficient C in any upper bound. And I try all, for each lower bound beta, I try beta z equals beta plus I. So basically this way I encounter all possible integer values which lie between the bounds but which are not in the gray shadow. An example again. So what do we have here? Again, the three inequations which we already knew. And if you look at the integer solutions, then we see there are two integer solutions inside. But these were not found by the dark shadow. So what we do is we eliminate y. Eliminating y had from this lower bound, this means this is my beta, b times y. And I have upper bounds. I go back here to the exactly here. So if I have lower and upper bounds, then I take the largest coefficient c in any upper bound, and then I compute this one. And in our example, the largest coefficient c in any upper bound is 3 here. So I will just apply that equation with c equals 3. And then I get these areas which are shown gray in my example, this one. And you see that here I have this value 1 and here I have this value 2 in the between the bounds. So I will try all, and then I will find actually for both 1 and 2 there exists also an integer value in the y dimension. So these two are the solutions, and I will find also both. If I am only interested in satisfiability but not the set of all satisfying solutions, that I can stop at the first pass, first value for I, where I find an integer solution, and this would be in this case y equals 1. And there I could stop. If I continue, then I will also find for x equals 2 the next one. So for I equals 1, I will find the first one and then also the second one. So I have also another example, which is, I'll just check how complex the gray shadow is. Actually, this is only containing only 2 of the constraints here. This is already tested. We will put it into the L2P room, so you can look at the complete example from eliminating the equations over the real, the dark, and the gray shadow. Do you have any questions? Good. Then if it is not the case, then what we will do perhaps the next time on Thursday, because it is only 1 hour, we can discuss how we can embed. Now we know quite some decision procedures for real and integer linear arithmetic. How can we embed it into SMT solving? Which conditions must be satisfied? And then if that is done, then I will think perhaps we will do some interesting decidability results on if you go on and you do not have only linear expressions, but you allow also multiplication. And then in the rest of the time, we will look at decision procedures for the nonlinear real arithmetic. And we will also look at some applications, and we will look at some tools that you can use. then thank you for your attention.